Ciao Davide, ciao a tutti.
Ciao Stefano.
Ciao.
Ciao Giorgio.
Ciao Stefani.
Ciao Stefano.
Ladies and gentlemen, it is my real pleasure to invite you for the final sixth and last talk of the webinar
Ora si
series
registrerà la
about
conferenza.
Geo-storage. This afternoon, we have the pleasure to have with us Professor Philip Ringrose, which is a person which has a long-lived experience. He's been one of the first to introduce this technology, I will say, certainly in Europe across the technology at the time of Statoil in the Sleipner field. And of course, he will give us a very nice overview of the topics. Before I let him the word, I have to wrap up a little bit with the nice experience of the webinar. As you have seen, we had the chance to have so far at least 5 talks proposed by very young researchers, which are at the frontier of the science on these topics. You have seen across the previous 5 weeks that the subject that we've been facing on this aspect are related both to the modeling, to the experimental geomechanical geophysics presented by Suzanne Hanks, which is based in Utrecht. Then we had the colleague Juan Alcalde, which is an expert on the risking aspects of this technology. Heinemann, which has been working, is still working in Edinburgh on the hydrogen storage aspect. Romain Chassani, which is an expert on history matching. Then we have been last week meeting Chiara Boschi, which is the champion in Italy of the mineral carbonation. So she gave us an overview of the themes. And today I think it was a very good idea to close the subject and the theme, having an overview of what it is a CO2 storage project and this global scale up in the next future. So this is essentially the theme, the topics that Professor Philip Ringrose will introduce us. Let me give me a little bit of short introduction, although it doesn't need to be introduced, I have to say, but Philip Ringrose is now a professor at the Norwegian University of Science and Technology in Trondheim, and he has a PhD degree in Edinburgh and Strathclyde. He's been working a lot on the reservoir model design, and he's been as well a scientist within the Equinor Research Center for a long time. nowadays very well known as Petroleum Geoscience Chief Editor as well. So he has, I would say, quite solid. He is in a rare position to have an overview of the topics of what we call this kind of energy transition. I think this is it, Phillips. I leave you the word, and
Sure,
thank you very much for your
thank you for the
presentation.
invitation, David, and it's a pleasure to be speaking to the Italian Geological Network. I'm honored. Are you seeing the screen okay?
Yes.
Great. And yes, I'm sitting up in near the Arctic Circle in Trondheim, but I have been to Italy many times. You have a beautiful country, and I wish I could visit you more often. So what I will do is I will talk a little bit about CO2 storage project design in totality. I will talk about the engineering aspects as well as the geoscience aspects, and then think a little bit about how do we take this technology into the future for the energy transition. Let me just check the progress. This is the famous picture of the Sleipner project, which has been used by many, but looking at Sleipner from the point of view of the pore space in the ground. So the issues I'm going to take you through in quite a fast kind of walkthrough, and I appreciate you've had some real leading scientists on different aspects of CO2 storage, so that's great. I'm going to try and look at the big picture. The phase behavior, the plume monitoring, some pressure issues, the flow dynamics of CO2, and what I call geological surprises. And then I'm going to, second part of the talk, I'm going to talk about a framework for thinking about the future of CO2 storage. And I've got this picture of Albert Einstein. There's a little bit of physics. It's important to have some physics, so I will introduce some of the basic physics, but quite a lot of the engineering, the practicalities of how we do this thing, okay? So it's a mix of physics and engineering, but then I'm going to bring in the geology theme as we go as well. So don't worry, if you're a geologist, there's some geology in here as well. So roughly speaking, a CO2 storage project looks like this. There has to be some kind of supply of CO2 where we need to know the flow rate, the pressure, and the temperature. Somehow we're going to get this to the wellhead. We will then know the wellhead pressure, the bottom hole pressure, and there will be some shape of the plume into the trap. And then we will want to see how the pressure evolves as a function of distance from the well and pressure as a function of time. And the yellow part is the injection period, and this part is the post-injection period. And all of this is simplified, but it's telling us the questions that we need to address when we are designing or planning a CO2 storage project. And I have to give you my little book plug here, but last year I published this very short textbook with Springer, which is a summary of my course notes to NTNU, where I teach this subject. And it's trying to make this material accessible to all. So this is an online book, as well as a paper copy, and you can see more details there if you want to. So the first project to mention is the Snøhvit project. This started after the Sleipner project in 2008, but is also very long running. And it's interesting because it is combining an onshore capture plant with offshore storage. And when you look at the emerging projects in the future, this is a very relevant project. The CO2 capture is combined with a LNG plant. So the project is selling liquefied natural gas to the market. And to do that, it has to remove some CO2 from the natural gas. And that CO2 is separated and then transported offshore and injected into an aquifer near the gas field. And one important thing about this project, it was the first offshore CO2 pipeline. And there was quite a lot of work to test, validate, and demonstrate this aspect. So here is a picture from one of the early papers by one of my colleagues, De Koya, on understanding the heat transfer for this pipeline. Because when we get into the phase behavior of CO2, we need to understand how that CO2 will behave in the environment. In the seawater, the outside temperature is about 5 degrees centigrade. and then we could use that to try and understand and design the pipeline, which I'll get onto in a minute. This is not my area of expertise, but I'm just reminding you that yes, you need to design the pipeline to get the CO2 to the site. In the Northern Lights project, which is now in the construction phase, and you see here the website where you can find a lot of open access information about this project. This is a mainly Norwegian government funded project with participation from industry. The companies Equinor, Shell, and Total are in a joint venture to develop the transport and storage part. And then 2 capture projects, a cement factory and a waste recycling plant, are involved in the capture. And the CO2 will be shipped from the Oslo region 600 kilometers to a local receiving site, which is here. And then from the receiving site, there's a pipeline going offshore to the seabed wellhead, and then into the geological formation below. And you can see already that this project has some similarities to the Snøhvit project. So we've used a lot of the knowledge from the previous projects to design this project. The phase 1 capacity of the Northern Lights project has a 1.5 million ton capacity, and it is now confirmed for construction with the investment decision having been passed. The shipping concept is 1 ship per capture site, and the volume per ship is 7,500 meters cubed of CO2 per ship. So we've also designed the capacity. This is not a huge ship, it's a medium-sized ship. And one of the concepts is that if we add new capture options to this, then we will add more ships. So it gives us a flexibility in the scale up. The pipeline is 12-inch, which is a bit larger in diameter than the Snøhvit 8-inch pipeline, and that gives us potential also for scale up into the future. And this project has developed a very interesting concept, which has sparked a lot of interest, which is the open storage facility concept. And they're basically saying to potential emitters of CO2 around Europe or Northwest Europe, would you like to give us your CO2? And this is ongoing, and we already have many projects that are considering sending their CO2 to this project from, for example, France, Belgium, Sweden, Netherlands, etc. So that's like a little bit of the context of the projects. But now I'm going to go into a little bit of the details of understanding how this project works. So the first thing, when you look at CO2 storage projects, you need to think about the phase diagram. And we as human beings on the surface, we experience CO2 as a gas. So at surface conditions, CO2 is a gas. But when we compress it into the subsurface, we move into the liquid phase or the dense phase. And what's interesting about the Sleipner project is the wellhead pressure is very close to the critical point of CO2. And by the time we get into the bottom hole pressure, we're into the dense phase. But then the CO2 is cooling in the formation back towards the critical point. And all of this means is that the density and the in situ properties of CO2 at Sleipner are very variable, and they have to be very carefully understood. At Snøhvit, which is a much deeper project, we are well into the liquid phase, and at the bottom hole pressure, it's very hot formation at 2.5 kilometers depth. And then the CO2 is heating into the formation. So it's moving in the opposite direction, getting warmer into the formation, but then potentially the CO2 can cool the formation. So we could have some thermal stresses. And between these 2 projects, we understand a lot about the range of expected behavior in the subsurface. And again, you know, I'm not an expert in this field. There are many others that are very good at understanding phase behavior. But what we've learned in these projects is that the thermal gradient can be quite important, and it changes the density of CO2. This diagram you see here is for pure CO2, but if we add minor components, like a few % of methane, then we will change this phase behavior significantly. For example, adding 5% methane will shift the critical point by about 3 degrees centigrade. And for reasons of corrosion, we also have to work hard to keep the water content or the aqueous phase very, very low, like 100 ppm level. So those are the sort of initial parts of the design. And then if I move on to the Sleipner project, well before I was involved in this project, they designed this CO2 injection well. It is a fairly high angle horizontal well, sail angle of 83 degrees. The main reason for having a horizontal well was to get the CO2 well away from the gas platform, but also underneath the geological target. And the steel components were chosen to be high chromium to minimize corrosion, and that proved to be a very good decision. But it's easy to say, well, it's gone well. We have 25 years of injection at Sleipner, but actually the first year was quite challenging. There was problems due to sand influx into the well, and the well had to be reperforated. And the sketch here shows you the reperforation situation, where we installed a gravel pack with sand screens to ensure good injectivity. And we saw the fluctuations between the expected injectivity of 2,000 meters cubed per day per bar, dropping by a factor of 10, but after the workover, we came back up again. And the reason why I show this very often in presentations is to remind people that, you know, the design part is important. You cannot expect a well to work perfectly from day one, especially if the geology is unpredictable. And therefore you need to expect some surprises. And the surprise at Sleipner was sand collapse into the well, but a solution was found. And now the well has been injecting for nearly 25 years, somewhere between 0.8 and 1 million tons per annum. It varies. And the cumulative now by last year was over 19 million tons stored. So it's a very large project. Geologically, we're injecting into a very thick sand package, about 200 meters, probably shallow marine deposits, but there's some discussion about the geological depositional environment. This is the top structure map, two-way travel time. And we are injecting underneath this structure, but we also see over time that the CO2 migrated to the next structure. So the CO2 is contained within these two dip closures. And the complexity of what happened in the storage zone is very interesting and is revealed by the time-lapse seismic imaging data. And I will say in a minute how this is actually publicly available data, but this is a very nice 3D reconstruction of the time-lapse seismic data produced by a gentleman called Anders Skjær, Norwegian name, and he made a very nice interpolation of the plume to work it out. And basically what we have at Sleipner is 9 layers of the plume. The topmost layer, layer 9, is very much easier to image than the lower layers, but with careful work on the seismic data, we can reconstruct all the multiple layers. And this data has 2 main values. It is showing us that we know where the CO2 is, so it's a kind of a validation process, but it's also given us a lot of insights into the behavior of CO2. And you know, the details of this plume evolution is still very hard to understand. So it's still a very much an alive data set that we can use to understand CO2 storage. A few years ago, Anna-Kari Furu here published a kind of review of the monitoring. And she asked the question, what was valuable and how did the monitoring meet the regulations? And one thing to understand is that when the Sleipner project started, there were no regulations for CO2 storage in place. The project was licensed underneath the petroleum law of Norway. And by the time the European directive on CO2 storage came in 2009, it eventually was put into Norwegian law in 2014. And then in 2015, the site was re-permitted underneath the new law. And this process was a learning process, because in the early phase of the Sleipner project, we were very much in the learning mode, and we were using research data to try and understand the process. But now we're in the fully operational mode. We can review the data and say, well, what was useful and what was not. And basically, in a simple way, is the seismic data is very important for conformance, but it also has a contribution to containment verification to show that it is not leaking. The gravity data is complementary to the seismic data, but in addition, there were visual monitoring at the seabed to sample gases and waters to try and understand environmental setting at the seabed. So this is an important story, and you can read all about it in the paper, but it's also a matter of learning what information do you need to monitor a CO2 storage site. I'm moving quickly on to the Snøhvit project, which, as I said, was deeper. And one thing we had at the Snøhvit project was a downhole pressure gauge. So in the middle plot, you see pressure, bottom hole pressure, as a function of time at the Snøhvit project. In addition, we collected some time-lapse seismic data, which is shown here. And we had a number of challenges with the pressure at Snøhvit. Initially, we had some pressure fluctuations, which were interpreted and almost certainly due to salt dropout effect. When you mix dry CO2 with a salty brine, you get a reaction and a precipitation of salts. And then there was a lot of speculation about how important this effect was. Well, in this case, a real case, we could see that, yes, it was important, but we were able to modify the injection by adding a monoethylene glycol solution to change that effect. So that was solved early on, but then the pressure carried on rising, and the continued pressure rise was due to a geological factor. And initially we were injecting in a fluvio-deltaic reservoir, and we think that there were geological barriers that were affecting this pressure rise. We then shot the time-lapse seismic data to try and work out where the CO2 was going, and we could see that most of the CO2 was going into the lower layer and much less into the upper layers. So there was a spatial distribution problem. But as I'll show you in the next slide, there was also a 3D effect of how far the CO2 is moving due to geological barriers. And we then, in 2011, changed the injection plan to inject at a shallower level, which was also a shallow marine depositional environment formation. And that formation was, in the long run, much better for injection, and we continue to inject in this other formation. So what the project here particularly showed us is that if you're designing a CO2 injection well, you need some flexibility in where you're going to inject, because you can never predict exactly what the geology is going to be like. So having the ability to change where you inject is an important factor. And what we could do in the Snøhvit case was we tried different injection completions down here, and then we switched to a shallower one later on. And that was actually part of the original design. So in this sketch, I show you that in a geological cross-section. This is the fault block that contains the gas field. So we were injecting in a neighboring fault block, which is water-filled. Initially, we were injecting into these lower completions in the two-borne formation, which is the fluvial deltaic sandstone. And then we switched to injecting into the shallow formation, which is Stør formation in Norwegian, which has better lateral connectivity, but it's still faulted. So we learned a lot about how geology interacts with the CO2 injection well here. And if I move on to this sketch here, this is, if I just split by here, so the next picture is going to show you a seismic reflection map down at this two-borne level where we started injection, okay? So now we're looking at an amplitude map down into the reservoir. This is the fault block that we're injecting into, and here is the injection point. And when you look at the seismic amplitude map, you can sketch on here, and here a geologist has drawn on an interpretation of the geology. We know we have a fluvial environment, and we think we have distributary channels coming in here, and probably a mouth bar around the injection point. And you could not predict all of this detail before you started injection, but you had to be able to respond to it. And what we found in understanding the pressure data is that probably these nearby stratigraphic barriers acted as a sort of partial barrier to the CO2, and the faults were acting as a more distant barrier. And we can see the fault on the pressure data, and we can also see these nearby barriers on the pressure data. So it's actually quite a complex compartmentalization situation. And again, it's a bit like Sleipner. You learn some things about your injection horizon as you inject, and then you have to be able to respond by adapting your well plan. And what we've learned from all of these projects is the need to be able to adapt your well design to the geology as you discover it. You cannot predict everything in advance. And these insights have been very useful for us planning future projects. This slide I've pinched from a nice paper by Williams and Chadwick, where they have modeled the CO2 distribution at Sleipner. There are, I don't know, many tens of papers, maybe even 100 papers on modeling the CO2 distribution at Sleipner. This is the top layer. The black is the outline from the time-lapse seismic data, and the colors are the history match from Williams and Chadwick. And they're showing, yeah, they can get quite a good match to the data. They looked at the sensitivity of temperature effects in here, but they also looked at the geological effects. And since I think we have many geologists on this call, this is their interpretation of some linear features from the isochore mapping. And we think these linear features, they could be fluvial channels, or I think they're probably shallow marine bar forms. But it's clear that they influence the migration of the CO2, which seems to go along those features. So there's a lot of interest in how geology has affected the spatial distribution of the plume at Sleipner. And you could look at this paper example to find out more. And then just so that everybody can play, as part of the open data sharing concept, a few years ago, we launched this data portal called co2datashare.org. It is available to the whole world. You have to sign a confidentiality agreement, but apart from that, you can download the data. And it contains this 2019 benchmark model, as well as the seismic data. And the purpose of sharing this is really so that we can build and develop CO2 storage competence globally. So, you know, the point is to learn from this data set. But then I'll just summarize what we know. And I know you've already had some talks on this process, but this is one of my simple sketches. When we inject CO2 into a geological formation, it will slowly migrate up dip, and it will tend to gather towards the top of the unit. And this is what we see at Sleipner, and it's what we see at Snøhvit. And then it will fill a structural trap. But as it migrates, it will leave behind some residual CO2, but there will also be some mixing with the brine in a convective or diffusive dissolution process. And we're still trying to understand those processes better. So when you go to real projects, what you can do is to try and quantify how fast do those processes happen. And this is a nice summary of some of the data at Snøhvit project. So this is now this shallower stir formation. This is an example of the time-lapse seismic data, where we can see roughly where the CO2 is going, but only in a crude sense. But we can see it is probably migrating up dip. This is a high-resolution reservoir simulation model, where we can see we can predict the details of this upward migration of the CO2, and we would iterate between the time-lapse seismic data and the reservoir model to try and understand that process. And roughly speaking, these real projects, they give us valuable calibration data to understand how CO2 behaves in the subsurface. And this is a continual learning process. But ultimately, they confirm the theory is broadly correct, but then we need to get the parameters right for forecasting. And I try and summarize the physics. I talked about Einstein at the beginning, but I'm not a physicist, I'm a geologist. But I think it's important to understand some of the physics. And this is a nice paper by Ocwen et al., which explains that when you inject CO2 into an aquifer, the behavior of CO2 is controlled by the mobility ratio. You're pushing a less viscous fluid into a higher viscous medium. And this is an unstable mobility ratio. The ratio could be anything between 5 and 20. Which would suggest that the efficiency of the process is between 5 and 15%. in terms of the portion of the pore space that is filled by the less viscous fluid. But when you bring in the gravity ratio, so this on this axis you have the gravity to viscous ratio. As you allow gravity forces to have an effect, you come into this domain. So that real CO2 storage projects should probably operate between, say, 7 and 3% storage efficiency. And when we look at the Sleipner data, after 20 years, our total storage efficiency at Sleipner is about 5%, which is in the middle of the expectations, but it also tells us a lot about how that process behaves. And in this sketch, I'm just showing you in a very simple way how that process works. From theory, we expect this plume to rise, and it's determined by the mobility ratio. But as you introduce more gravity forces, there'll be a tendency for that plume to go even faster to the top and then fill the structural traps. And it's this interplay between viscous and gravity forces, which is quite important if we're trying to try and forecast this behavior. And the way we've done it, and this is showing you one example from the Sleipner time-lapse data set, which you can find on the CO2 data share, is using that time-lapse amplitude data. So there's layer 9, there's layer 8, there's layer 5. We can try and calibrate that behavior. So the idea with the modeling data set is that there's a model of this whole domain, and that we would use the time-lapse seismic data to try and calibrate that model. And as I said before, this data set is very valuable in confirming to the general public that CO2 storage works as a general concept. But for the scientists involved, it gives us really important insights into the physics of that process. How fast does it migrate upwards? How fast does it expand laterally? What is the fractionation between the mobile phase and the dissolved phase? And I confess to you that the physics of this process is complex, but we're learning a lot as we go. So that's a really fast walk through what we know about CO2 storage projects from these case studies. We know roughly how much CO2 goes into a well, somewhere between 0.3 and 0.9 million tons is the experience so far. We also know that injectivity and capacity is very dependent on reservoir properties that we learn about as we go, which means that we need some flexibility in the design. So to summarize, you need to think about well management and placing of the well. You need to use monitoring data, and it's an iterative process to sort of learn about CO2 storage projects as you go. So that's the first part of my talk. I'm going to move very quickly on to the question of global scale up, and then we can take some questions. At the moment, probably you know this already, there are 20 large-scale CCS projects in operation. Many of them use CO2 EOR, but quite a few of them, and an increasing number, use saline aquifer storage. So then I want to ask the question, okay, 20 projects, is that enough? How much do we need if we're going to address the climate challenge? So just before the pandemic, Tip Meckel from University of Texas and myself, we tried to address the global problem with this paper we published in Scientific Reports. And we looked at the global offshore basins, and this map shows you the gravity data for all the world's offshore sedimentary basins, the red and the orange, and the distribution of oil and gas fields. And we asked the question, let's think big. We have been a petroleum-dominated society for the last 50 years. If we become a green society with zero emissions, what do we need to do for CO2 storage? And the answer we came up with is that by 2050, we're going to need 12,000 CO2 injection wells. And I'll explain to you how we came to that conclusion. And what we did is we said, let's think about oil and gas basins, not from an oil and gas point of view, but from a CO2 storage point of view. And the oil and gas industry has collected a lot of data. We've drilled a lot of wells. So for example, in Norway, we can get a general trend line for the lithostatic pressure, the hydrostatic pressure, and the fracture pressure. from published data sets. And we can do the same with the Gulf of Mexico, and we've compared these. And at a very crude level, the basins behave very similarly. You can also see that most basins have hydrostatic pressure down to about 3 kilometers. And then as you go deeper, we have overpressure. So the initial pressure would be higher. And we would then say, from a storage point of view, the domain we want to store is typically between 1 kilometer depth and 3 kilometers depth. Usually this is the hydrostatically pressured zone, and we must avoid increasing the pressure to the fracture pressure. So we use this as a framework to assess the problem. And then we say, okay, there has been a lot of mapping of the storage resources. So for example, the North Sea Basin has a mapped resource of 160 gigatons for CO2 storage. North America, even bigger, 2,000 gigatons or more. But we've only done a tiny amount of storage so far. So then the question is it realistic to scale up? And what we said here is that, okay, in the oil mentality, you explore for oil, you find an oil field, and you produce the oil field, which is usually under buoyancy pressure. And then you would get some natural pressure depletion. But the CO2 storage problem is that we're going to start with hydrostatic pressure, and we're going to gradually increase the pressure to some degree as we inject CO2. So it's a kind of inverse problem. We're not producing a fluid, we're injecting a fluid. So how would that work? Ultimately, we want to avoid exceeding the fracture pressure, but in many formations, we have depleted pressure. So there are some cases where we have pressure lower than hydrostatic. And this gives quite a broad range of pressure conditions, which we need to understand. And again, to make this problem as simple as possible, we said we can generalize this and say, well, in any reservoir, there's going to be a fracture pressure, which you do not want to exceed. There's going to be your bottom hole well pressure, which will be at some degree below that. And then you have your initial reservoir pressure, which will gradually rise as you inject CO2. In the storage geometry A, it rises slowly, but it never becomes too high. So you have a situation where the project is not pressure constrained. But in storage geometry B, you have a situation where the pressure is rising quite rapidly, and you have to stop injection because you're getting too close to the limit. And in a way, the early phase of the Snøhvit injection was a bit like this, whereas Sleipner has behaved like this all the way through. But we're using this as a model to try and work out how would projects behave in the future. We also collected the injection data from the existing sites to get a sort of empirical database. So this is the range of known CO2 injection rates. And if we look at the offshore wells, we are a little bit higher. Our average CO2 injection rate from the database is 0.7 million tons per year, with some variation around that. And of course, the lower rates will be related to pressure constraints, and the higher rates will be related to open conditions. So we went through these scenarios and we tried to treat it stochastically in the model. And then I'm coming quickly to the answer, or the end of the study. We then took historical well rates from Gulf of Mexico and Norway and Texas. So the dots are drilling numbers of wells from a historical database, and we pretended that those wells are drilled into the future from 2020. And this gives us a kind of model for industrial development for CO2 storage. And then we could use the well rate to map to CO2 injection rate using those statistics for how much can you inject per well. And then the solid lines, they show you the probability distribution for CO2 produced. And then we come up in total with the answer that the number of wells needed for the 2-degree scenario, which is approximately 7 gigatons of injection by 2050, the number of wells is 12,000, with a spread, of course, because it's a probabilistic model. And that gives us a kind of framework for what would CO2 storage look like into the future. And if we split that down into different clusters, so just think about Europe now. So think of Europe as a cluster. How many wells would Europe need? Well, if Europe is 1/5 of global emissions, it's probably a little bit less than that. in the next 10 years, we'd need 200 wells. And by 2040, we need 1,000 wells. So, you know, this is the point of this is to say it's not that many wells to reach the targets of the Paris Agreement, which is limiting global warming to 2 degrees centigrade. It's also important to say that this is only the CCS part. You still have to do renewables and energy efficiency and all the other actions needed in the decarbonization metrics. But the main argument we're making is that this is a very achievable objective, and we should devote our energies to doing this thing. And then I'll just show you this study. I was involved through Equinor in a major study for the north of England, where we looked at turning natural gas to hydrogen for decarbonizing the whole of the north of England. And there we had to design offshore storage to meet a target of 17 to 18 million tons of CO2 injection per year. And the number of wells we needed in this outline design was 12 wells from 4 subsea templates. So again, you know, this is a realistic objective. And actually in the UK now, there's a project called the Northern Endurance Partnership led by BP with Eni, Equinor, National Grid, Shell and Total all involved to develop this for the first projects. So this is actually also, you know, in development. I think I've used my time, right? So this is my summary, and then we can maybe take some questions at the end. What I've tried to show you is an overview of the design for wells, reservoir management. I've reminded you that geological heterogeneity means that we need to be flexible when we design these projects, and that you need a fit-for-purpose reservoir monitoring program. And then we've tried to use historical well rates to sort of imagine what the future would look like for a totally decarbonized society by 2050. And our estimate is we'd need 12,000 wells globally to achieve that, which is very realistic. So you need a bit of physics, you need some engineering, wells, pipelines, and don't forget the geologists. I know there are many listening now. You know, you also need geoscience. You need to characterize and understand rock formations. This is an image of an outcrop, which is an analog to the Sleipner Utsira formation. And we obviously need to understand geological systems as part of this. And when you put all that together, you know, it makes a kind of exciting project for subsurface geoscientists to get involved in. There's obviously a lot of questions about how fast CCS will move in our societies, but you know, I like to think of this as it's a problem we know how to do it. We just need to get on with it and do it. So that's it for now. I'll take some questions. Do you hear me? Stop.
David Jacopini, your microphone. David, your microphone. We can't hear you.
Can you hear me?
I can hear you.
Yes, okay.
Okay, so sorry, I had a slight problem. So thank you very much for your talk, Philip. Very interesting, especially also the second part with some interesting vision for what should be done or what could be done in the future. I think now it's time to take questions. So anyone in the audience willing to ask some question, or anyone writing question on the chat, I will take the question or call him directly. So there is already a question. I will call directly the person, which is Domenico Chiarella. Are you around?
Yeah, I see it. Yeah. You're saying, hello, Domenico. You're saying what additional aspects should we consider in tectonically active areas like Italy? I like this question. Yes. So I haven't mentioned this, Domenico, but there is concern about does CO2 injection stimulate earthquakes? Sure. And there's been a lot of discussion in the science media about that. And in the Norwegian project, we have actually put in a microseismic monitoring network so that we can have, you know, a good database for recording microseismicity. There are probably 3 or 4 projects around the world with good seismic monitoring for CO2 injection sites. And it's kind of slightly unknown what the final answer is. But what I would say is that as long as we're not exceeding the pressure very much, like a small pressure increase is not expected to have significant earthquakes. But each site has to be investigated, and you know, yeah, seismic risk is a factor that has to be considered. I agree.
Hi, Philip. Just to follow up on that, and what about natural earthquakes? You know, in places like Italy or any other active area where, so it's not strictly related from the induced earthquakes, but
Yes.
if we have a natural earthquakes, how can we
So
risk in our
How can we
evaluation?
risk that? Yeah. Well, there's one very useful case study from Japan. There's a small pilot study where they injected CO2 into a formation, which then experienced a natural earthquake of magnitude 6.5. So the ground acceleration was quite significant. And they were able to show that there was no impact on the subsurface CO2 in a real case. And they were measuring the pressure. So there is one case study in Japan of how would a CO2 storage domain respond to large earthquake shaking. You know? So,
Okay.
but you know, more work to be done, no doubt.
Yeah, thank you very much.
There is another question on the chat. Leonardo Del Sole, are you around? So you can probably directly ask you the questions. Leonardo, are you around?
Yeah. Can you
Hugo.
see me?
Yeah, yes,
I can hear you.
Thank you for your presentation. Very interesting. So my question is, if you ever faced CO2 leakage problems, and if you did, what were the geological factors that controlled the leakage, and how did you solve it?
Yeah, it's a really good question. And, you know, there are several, we could say, alleged leakages at CO2 storage projects, which were then investigated. One in Canada and one in Norway, where when you suspect a leakage could have occurred, then you have to work out what is the composition of the gas leaking. And the most promising technology there is using geochemical tracers so that you can tell the difference between natural CO2 and human stored CO2. But at the moment, we don't know of any leakages that have occurred. We have documentation of natural systems which are leaking CO2. So, for example, in Italy, you have many CO2 seeps in volcanic areas where the CO2 is bubbling up from a volcano. And we can use this to try and understand the processes. So I would say the biggest problem with leakage is how do you differentiate possible leakage from natural leakage? But probably the biggest risk for CO2 storage projects is the leakage associated with what we call legacy wells, old wells that might have, disturbed the formation. They are one of the bigger risk factors. And that is an ongoing discussion. How do we handle possible leakage up old well paths?
Okay, thank you.
Yeah.
Very good. We have another question from Alessandro Iannacci, which is a couple of meters from my office there. Alessandro?
Yes, I was wondering how much energy in terms, of course, of CO2 consumption we will need to store to build these 12,000 wells and to store all that CO2.
Yes, no, it's a very good question. So thanks. And it is true that a CO2 storage project, the biggest demand on energy is the compression of the gas at the surface. So it is the biggest energy demand. We can obviously try and make it more efficient. I think in terms of energy consumption, I don't have a number on the number I do have is that for the Northern Lights project, they looked at the whole LCA, the life cycle analysis for the whole value chain, and they estimate about 15%, 1/5, for the total life cycle emissions of the transport, compression, and storage part. So if you want a rough figure, the energy used is about 20% maximum. But there are many ways that we can bring that down. And we could use, for example, renewable energy to do the compression. So there's no reason why a CO2 storage project couldn't be a zero emissions project. But of course, the main objective of a CO2 storage project is to store captured emissions from other sources.
Yeah.
So, you know, you should not go away thinking, oh, well, it's not worth doing CO2 injection because you use a lot of energy. No, you use some energy, but overall, you're injecting very large volumes of CO2 in the subsurface. So, you know, it's an energy that's worth spending.
Okay. Good news.
Yeah.
Philip, I will ask you a question just attached to that one, which is a question I've asked to all the speakers across.
Yeah.
And the main question is about that. Who is paying that? Who is going to pay all of that? Because we are speaking about a technology which now is costing money to the industry, which has to go in a transition, which will cost additional money in order before to set up to this direction.
Yeah.
So who is going to pay that?
Yeah. And that is, you know, a question I cannot answer because it's a socio-political question. But let me answer it in this way. In Norway, the reason why we have 25 years of experience at Sleipner is that Norway put in a CO2 emissions tax way back in 1991. So in the Norwegian society, it's not permitted to throw your CO2 into the atmosphere. If you do, you have to pay the tax, which is approximately just over 50 euros a ton now. So the Sleipner and Snøhvit projects are economically viable because there's a tax system in place in Norway. But then different capture technologies have different costs. So if we were to make CCS, you know, economically viable around the whole planet, you might need to get a CO2 tax up to the 100 euros level, okay? And you think, well, is that reasonable? Well, I think so, because, you know, this is huge value to our society. The value is saying, let's have enough CO2 emissions tax to make carbon capture and storage a viable business. And that is good for our societies. So what you're looking in the European Union at the moment and in many of the component countries is that there's a debate about which financing mechanisms will be put into place.
Oh, yeah.
In California, for example, there's a clean fuel standards, which is of the order of $200 per barrel. You know, there's a premium on clean fuel, and that actually is enough to drive CCS. So I think you have to turn the question around. You don't have to say, how much is all of this going to cost and who's going to pay? You say, our society does not want to emit CO2 to atmosphere. What price of CO2 do we need to make that happen? That's the better way to answer the question.
Very clear. There is another question. I'm following the screen. It's Carla Romano. I don't know if she's around. Carla, are you around? Oh, I mean,
yeah, I'm
really
here.
Perfect.
Hello, Carla.
Go ahead.
Hi. So my question is mostly related to mineral trapping and CO2 like captured through carbonization. And I was wondering if in your model prediction you had included a quote related like that. And mostly is a question that it's related to what do we need to do as a scientific society, because like CO2 carbonization, like capture through mineral trapping is such a slow process and probably it's like a limited amount that we can actually store. Should we focus in the near future on just like solving these issues related to pressure management and saline aquifer, or should we still also focus on understanding better and improve the mechanism of mineral trapping, of CO2 mineral trapping?
Yeah, it's a really good question, Carla. And you know, how should I address this? There is an interesting project in Iceland called Carbfix, which is injecting CO2 and water into basaltic formations. And they have argued that about 70% of the CO2 can be turned into minerals in the short time frame. So there are rock formations which have a very rapid mineralization rate. However, in a sandstone aquifer like the Utsira, the mineralization rate is very, very, very small. But there are formations in between. For example, you point out of carbonates. So maybe some carbonates will mineralize a little bit faster, limestones, who knows? And the other thing I would say is that CO2 going into the water phase and CO2 going into the mineral phase is a really important part of stabilization of CO2 storage. So even if in a saline aquifer, the mineralization process is very, very slow, it's an important part of the long-term sealing, right? So at the moment, mineralization is a very small component, but in the long term, it could be significant.
Okay. Well, let's hope for that. Thank you, though.
Another question is by Mariano. Are you around, Mariano?
Yes.
Same line of the previous question.
Question, Phil, is this. I was thinking of Italy. If we need to inject into deep saline aquifers, not just in depleted reservoirs. In Italy, we have very little knowledge of the subsurface out of the, let's say, the Adriatic, where we have the depleted gas reservoir. But if we need to inject into deep saline aquifers that are close to industrial district, it will take time and money to build the knowledge that we need to run a project.
I really like this question because a simplistic view is often, we've got the CO2, what should we do with it? Stick it in an old gas field, okay? But that could have some challenges in terms of wells, infrastructure. But you make the point is that the problem with saline aquifers is that you don't have any information, okay? There's no history of exploration. So I actually think that the most useful way to proceed is to inject in saline aquifers near petroleum infrastructure. So if you have a basin that has had a history of oil and gas development, you have a lot of well completions, you have 2D seismic, you have 3D seismic, you have general knowledge of the rock formations. And that general knowledge is really important, right? It's kind of like regional knowledge rather than site-specific knowledge. So when you come to develop a particular CO2 store, you might need to collect some new data, but you're not going into the complete unknown. You're basing it on knowledge that you already have. And that's why I kind of like that global map that we published, is that you look at our world and you say, hey, for the last 50 years, we've been developing onshore and offshore basins for hydrocarbon resources. Let's turn that resource around into a place to store CO2 and use the knowledge we've gained from the historic petroleum industry into a future CO2 storage industry. So it's not as black and white as you maybe first think. But I agree with you, it's a challenge. You know, who pays for this data? You know, because at the moment, CCS is not economic.
No.
So we have to find a way of leveraging our existing knowledge as well as funding these carbon capture and storage projects. And that's not easy, I agree.
Yeah, I suspect that there is a massive work to be done by both scientists as well as a lot of part of the industry which are involved directly in a way or another in these topics, into create a proper perception on how we can build up on what has been done from a technological point of view, starting from where we already got infrastructure of those types, and therefore that the society is not made by black and white, in a sense of good industry, bad industry, but it's in reality from a pragmatic point of view, what may be done at the lowest cost possible in the most efficient way. And this is a message that has to go across, I would say, the younger generation as well. That's one very simple concept I used to say is that the energy for free doesn't exist.
Yeah.
The motus perpetuum, where a lot of scientists were speaking about a long time ago, doesn't exist. You have to pay. There is a cost.
Yes.
I like so, and that is where I suspect from both sides we have been probably underestimating the reaction in different areas. I mean, don't use Norway as a reference point. If you try to use, for example, a middle average news approach or a society approach across Europe, the situation is much more delicate. I would say Italy is facing exactly this problem.
Yes, the situation is delicate. I really like the way you summarize it. And I always, the discussion which is often becomes a bit hostile, it's too expensive, we can't do it, that kind of thing, or we don't like the fossil fuel industry. We need to turn that around and say, what kind of society do we want? We can get clean energy, we can develop renewable energy, and we can find funding mechanisms to make this work. So it is a more positive attitude, but each society has different views.
Yeah.
And I think one of the role of geoscientists is just to state the facts. This is, we understand the subsurface, we know the history of mining, oil, coal. We can change this discussion around and say, look, how do you want to use Earth resources? This is what it takes.
Yeah.
But I agree. The social factors and they're not easy to solve.
Interesting. Well, are there other questions, or someone else would like to ask some additional question? Otherwise, I think it's time to.
I think it's time to wrap up. But I
Yeah,
really appreciate the good discussion we had.
Therefore, I will thank you very much, all the audience, and I will say all the people who attended. We had a very impressive attendance, as an average of more than 100 people across the different two platforms, which has been quite impressive. A lot of questions to the various speakers. Therefore, for me, it's a real, I feel a little bit sorry to close this series, but everything has a start and has an end. And therefore, I thank you very much, the Società Geologica Italiana, for giving me the opportunity to use their platform. I will thank very much Fabio Massimo Petti and Raffaele Viola for their support from a technical part that couldn't happen without their support and their help. And thank you very much again, Philip Ringrose. Have a nice evening, and see you for the next probably series of talk, if there will be one. We never know. I'm thinking about. Thank you very much again, Philip.
Thank you. It's a pleasure, and good luck to all of you.
Yeah, and have a nice evening.
Ciao.
Thank you very, very much, Philip. Thank you very, very much, David. Ciao, Ste. Ciao a tutti.
Grazie a tutti.